In this presentation, we are going to solve our problem number 4 based on transfer function. So, let's get started. Find the transfer function of the following RL circuit. The RL circuit is given to us. The input voltage VIT is given to the circuit and the output voltage Vout is measured across the inductor. In the previous problem, the output voltage was measured across the resistor, and now in this problem, we have changed the arrangement and the output voltage now is measured across the inductor, and we need to find out the transfer function. So moving on to the solution, we all know that the first step is to find out the Laplace equivalent circuit. The input voltage VIS is given to the circuit, the impedance of resistor is R, the impedance of inductor is SL, and the output voltage Vout is measured across this inductor. And we know the resistor and inductor are connected in series, and that's why the voltage gets divided. So we can find out the output voltage which is measured across the inductor by using the voltage divider rule, and it is given as Vout is equal to VIS, which is the total input voltage, multiplied with the impedance of inductor, which is equal to SL, divided by the total impedance of the circuit, which is R plus SL. Now if we transpose VIS to the left hand side, we will get the ratio Vout over VIS, which is the transfer function, is equal to SL over R plus SL. In this way, the transfer function is equal to SL over R plus SL. So now we are done with the transfer function calculation for this RL circuit, and now we will compare the two RL circuits that we have discussed in the previous lecture and in this lecture. So moving on to the comparison between the two RL circuits that we have discussed till now. In this circuit, the output voltage is measured across the resistor, and in this circuit, the output voltage is measured across the inductor. The differentiating factor between the two circuits is the position of inductor. The impedance of inductor is equal to SL, and S is the frequency dependent term. So if we change the frequency, the behavior of inductor will change, and it will change the behavior of the circuit. Let's understand the behavior of an inductor. The reactance of an inductor, by which it opposes the flow of current through it, is equal to SL, and we know S is equal to sigma plus j omega. So S is the frequency dependent term, so we can say that the reactance of inductor is directly proportional to frequency. So for high values of frequency, the reactance of inductor will be high and it will behave as an open circuit. On the other hand, if the frequency is low, the reactance of inductor will be low and it will behave as a short circuit. So now we know that the inductor behaves as an open circuit for high values of frequency and it behaves as a short circuit for low values of frequency. So in this RL circuit, the output voltage is measured across the resistor and its transfer function is equal to R over R plus SL. We have calculated this in the previous problem. Now if we observe the behavior of inductor in this circuit, if we pass low frequency signal into the circuit, the inductor will behave as a short circuit and we will get some output voltage. But if we increase the frequency, the inductor will behave as an open circuit and the output will become 0. So we can say that for low value of frequency, the output is non-zero, and for high value of frequency, the output is equal to 0. In this way, this circuit behaves as a low pass filter, and that's why we call this circuit RL low pass filter. And its filtering characteristics is given like this. For low value of frequency, the output is non-zero because the inductor behaves as the short circuit. And for high values of frequency, the output voltage is equal to 0 because the inductor will behave as an open circuit. And if inductor behaves as an open circuit, in this particular circuit, the current to the circuit will be equal to 0, and that's why the output will become 0. So moving on to this circuit in which the output voltage is measured across the inductor and the transfer function Hs is equal to SL over R plus SL. Now, if we observe the behavior of inductor in this circuit, then for low frequency input voltage, it will behave as a short circuit and the output voltage will be equal to 0. But if we increase the frequency of input voltage, then the inductor will behave as an open circuit and the output voltage will not be equal to 0, it will be non-zero. In this way, for high value of frequency, the output is not equal to 0, and for low value of frequency, the output is equal to 0. And that's why we call this circuit as the RL high pass filter. Because for high values of frequency, the output is non-zero, and for low value of frequency, the output is equal to 0. The filtering characteristics of RL high pass filter is given by this graph. We can observe that for low value of frequency, the inductor will behave as a short circuit and the output voltage will be equal to 0. But for high values of frequency, the inductor will behave as an open circuit and the output will not be equal to 0. It will be non-zero. And the frequency at which the output changes from 0 to non-zero is called as the critical frequency. And in case of high pass filter, the critical frequency is the minimum frequency. Whereas the frequency at which the output voltage becomes 0 in case of low pass filter is called as the critical frequency, and in case of RL low pass filter, it is the maximum frequency. In this way, the position of inductor plays an important role. If we measure the output across the inductor, it will behave as a high pass filter, and if we measure the output across the resistor, it will behave as a low pass filter. So now we are done with this lecture. We will discuss some more problems based on transfer function in the upcoming lectures. Thank you for watching this lecture. I'll end this lecture here. See you in the next one.